All right, welcome back to Loving the Physics with Mr. Goldthorpe. Let's move on now to circular motion in Unit 5. And what's cool about this is we actually get a chance to kind of go down memory lane. If you remember in this course, we started with kinematics, then we went to dynamics with forces, and then we finished with energetics. And we're going to do the exact same thing now with this new area called circular motion. We'll start with kinematics. So the mathematical description of motion. And we're going to be studying something called uniform circular motion. So I don't think it'll surprise you that that means that this object should be going in a circle, big surprise, but to be uniform, it has to go around at a constant speed. And if it's going at a constant speed, well, that means that we're allowed to use the lovely equation v is equal to d over t. But what d and what t? So when you're doing a circle, the most natural distance to use is the distance for one lap, and therefore the time for one lap. Now, if you remember, the distance for one lap around a circle is called the circumference. So this becomes equal to 2 pi r. So that's the distance for one lap. And the time from one lap has a special letter in physics. It's very useful. We call it big T, where this thing called T is called the period. It is the time for one lap, one cycle, one repetition, one oscillation. The time for one lap. Now this equation, by the way, is actually on your formula sheet, so you don't actually have to derive it, but that's where it comes from. V is 2 pi r over big T. Now that's speed. But what about velocity? Now, as you guys know, the velocity is a vector. It actually has direction. And the direction of a velocity vector, as you can see here in the description, will always be tangent to the circle. So if we look at this object here moving around in a counterclockwise direction, and if it's going in uniform circular motion, then at one location it's going on the tangent, and there's the velocity at one moment. At the one on the bottom, it'll be go on the tangent, and the key thing is that this is going at a constant speed, so the length of this vector should not change, just the direction. And the same thing kind of up here at the top. So same speed, different direction. And it turns out that this velocity vector, the direction of it is actually very important because it tells you what would happen if the object was actually let go. For example, at the bottom there, if you let go of that object at the bottom, due to inertia, it wants to keep going in a straight line. So you could actually call this the inertial pathway. Objects don't want to go in circles. They want to go in straight lines. And so if you let it go, it will go on that straight line path, at least initially. And we call that the inertial path. So that is based on Newton's first law. Good. So that's speed and that's velocity. Now let's move on to acceleration. And we're going to be talking about a brand new kind of acceleration called the centripetal or centripetal acceleration. And what you'd realize is this is basically the change, like how quickly the velocity changes direction. We call it the rate of change of the velocity's direction. How quickly the direction is changing. So if you have a high centripetal acceleration, the direction is changing really quickly. And what you have to realize here, and as I'm showing you, I'll try the different color for this. The centripetal acceleration will always be perpendicular to the velocity and always towards the center of the circle. That's why we call it centripetal, center seeking. It seeks the center. So when you see that first part here that says centra, that means to the center. So in the diagram below, you'll see that the acceleration goes towards the center. There's our AC. And the same thing for all the others. And if it's uniform circular motion, all these ACs will be exactly the same in magnitude. They're just pointing in different directions because they all will point towards the center. Good, that's the direction of centripetal acceleration. But I guess the question is, why does it have to be perpendicular to the velocity? So what if we play devil's advocate and not have it going towards the center? What if we have an off-center acceleration? Well, what we can do in this situation here is we can draw the components for the acceleration because it's diagonal. So we bring in some axes and we bring in the two components. So we'll have this component, we could call that AX, and then we could actually draw the other one kind of right here as AY. Those are the two components of the acceleration, horizontal and vertical if you wish. And what you'll notice is, and I'm just going to highlight it for you here, can you see this part right here? You see how the acceleration is going opposite to the velocity? What happens when the acceleration goes opposite to the velocity? Answer, this would cause it to slow down. And you see that's not allowed for uniform circular motion. When it's uniform circular motion, it has to go around at a constant speed. And you can see therefore that that's not possible in this situation right here because of that X component. So to make it clear, if you want this thing to go at a constant speed, you cannot have that X component at all. So if I go and do some creative erasing, if I get rid of the X component, which basically gets me to get rid of this diagonal vector, and you're left with just AY, you can see that the AY, it's not going with the velocity, so it doesn't speed it up. It's not going against the velocity, so it doesn't slow it down. It just changes its direction. That's why it has to be perpendicular to the velocity. Good, hope that makes sense to you. All right, one last thing for the kinematics, and that is the equation for centripetal acceleration. So the equation we have is AC is equal to V squared over R. And I think everything's logical. So V is the speed, R is the radius. But the question is, does this make sense? Does this equation help us understand how quickly the velocity changes direction? Well, let's take a look at some relationships that we actually have here. The first one is a relationship between, let's see, AC versus V. So in this case, let's imagine that the manipulated variable happens to be V. That one's the one that we're changing. The responding variable happens to be AC, and the control, what we keep constant, is the other variable R. So that actually is held constant. If that's true, then we can now change this to proportion. We can say that AC is proportional to V squared. We call this a direct square relationship. So I'll tell you a couple things about it. First of all, the graph for this. If we graph AC versus V, it would be a square relationship, but basically a parabolic relationship, which looks like this. And we also should know that if, for example, let's say V gets multiplied by 3, can you see what would happen to AC? It goes through the direct square relationship. So it'll be multiplied by 3 squared. And what this is actually telling us is the faster the object goes in that circle, the faster it changes direction. Done. All right, let's try the other relationship. Oh, I guess, wow, I thought I had a bit more space than that. I'm gonna have to do something a little bit ugly here, and I apologize, but I'm just gonna add a page, and then I'll come back to this other equation here. Okay, here's the other relationship that we should be aware of. we do, let's say, AC versus R, like that. And again, we know, I'll put over here the equation. We have AC is equal to V squared over R. So in this case, the manipulated variable would be R. The responding variable would be AC, and now the control would be the other variable, which is V. So we're keeping it at a constant speed. Then in this case, now we change it to proportion, we have AC is proportional to 1 over R. And I hope you guys remember, that is an inverse relationship. So a couple things, the graph for this, here's our AC, here's our R, and it's going to be an inverse relationship. That. And that means that if R gets multiplied, let's say, by 4, can you see what would happen to AC? It would get multiplied by 1 over 4. So therefore, the bigger the radius, the smaller the rate of change of direction. It changes direction at a slower rate because it's a much bigger circle. Okay. So that's the relationships. Sorry about bouncing around here. You also have in your notes that there is another equation we could use for AC, which is 4 pi squared R over T squared. And just remember, T is called the period, the time it takes to do one lap. Okay, we finish up this part of our lesson by just doing a quick example. Okay, so here's a centrifuge question, just where we spin things like test tubes in circles. And I'm just going to draw this very quickly on the side here. Actually, I'll do this in black, let's say. So here we have our circle, our circular motion, like that. And then we'll just have our test tube, like that. So there's the test tube at some particular location. And we're talking about the end of the test tube. Let's just say that that is the end of the test tube right there. And we know the speed at the end of the test tube. So this speed right here is 85 meters per second. And we're trying to find the diameter, but I'll put on here the radius since that's important, and then we'll get the diameter from there. Okay, so that is our diagram if you need it. The most challenging part of this question, by the way, comes down to this 3,600 revolutions per minute, because we know that we're going to be using the formula V is equal to 2 pi R over big T. That's going to be our governing equation here. But I need to figure out big T, because I know the speed. I just need big T. So our job is to find the period. And the inspiration for that will come from 3,600 revolutions per minute. And we're going to use a formula that's actually on your formula sheet on the top right of your formula sheet. It is this: T is equal to the total time over the number of cycles, if you wish, or laps, whatever it might be, revolutions. So this is on your formula sheet. And this is very useful here, because the total time, this is 3,600 revolutions every minute. So if it does 3,600 revolutions or cycles, it takes a minute, which is 60 seconds. Good? And that's how we establish the period of oscillation. And this gives us about 0.01667 seconds. Okay, well now we can figure out the radius. That's our next job, is to find R. So we cross multiply, we get V big T equal to 2 pi R. Therefore, R becomes equal to V big T over 2 pi. So the speed was 85. The period 0.01667 all over 2 pi. And just make sure that 2 pi is in brackets on your calculator if you're going to do this all at one time. All right, let's see what we get here. So I get about 0.2255 meters. But I'm not looking for radius, I'm looking for diameter. And hopefully you understand the diameter is simply going to be twice that. So the diameter is simply going to be 2 times the radius. So 2 times 0.2255. So just multiply that by 2. You get 0.45. Let's see if it's 2 sig digs. Yeah, 2 sig digs. So 0.45 meters or 45 centimeters. Okay, well that is the kinematics of uniform circular motion. My recommendation is to go onto the homework and practice the ones that involve kinematics. If it ever talks about forces, don't do that one yet. That's our next part of our lesson. And I'll see you then.